Hi everybody, welcome back to Super Awesome Calculus. I'm Augie Kennedy, and today we're going to talk about linear approximations and differentials. Now, I know we're starting to already get into the applications, and I said that this chapter, Differentiation Rules, would be all about just rules of differentiation. But that's not really the way that Stewart chose to set up the book, so we're already going over some applications. Last time we covered an application called related rates, and I gave you a problem to work on. So let's go over that problem first, shall we? Alright. The question was, a cylindrical tank with a radius of 5 meters is being filled with water at a rate of 3 meters cubed, or 3 cubic meters per minute. How fast is the height of the water increasing? Now the first thing you might have done is you might have taken my advice and drawn a diagram. You could draw something, a cylindrical tank. I always draw something that kind of looks like a soda can. There you go. And we know that it has a radius, half the diameter, r is 5 meters. And we know that it's being filled with water. We know that there's its height, and it's being filled with water, and the rate at which it's being filled with water is 3 meters cubed per minute. Now what do we know? Well, we know that the water is filling up that thing. That sounds to me like volume. The volume of water in the cylindrical tank is increasing. And we know that it's increasing by meters per minutes, which is an increment of time. So just like the last time, we have volume, we have radius, we have height, which we don't know, and we have time. So let's try to relate all of these variables if we can. Well, it's pretty easy to do so if you remember what the volume of a cylinder actually is. And the volume of a cylinder is expressed this way. V equals pi r squared h. This circle down here times however high it is. This really helps because we have variables here. And we know that r equals 5 meters. So therefore V equals 25 r squared, 5 squared, 25 pi h. That's V. But we're not done yet. We know this. We know now that V equals 25 pi h. But we also know a rate. We know that it's increasing at 3 meters cubed per minute. That's volume. That's dV dt. And we know that dV dt equals 3. So what do we want to find out? We want to find out how the height of the water is increasing. How fast? Well, we've got height and we want to know a time, so we have dH dt. Alright? So now what we're going to do is we're going to figure out how to get all of these things related. So let's write down the important information. We know V equals 25 pi h. We know dV dt equals 3, and we want to know dH dt. So the first thing we're going to do, if you remember, is we're going to differentiate. It's very important to do this because that's how we're going to get dV dt. We differentiate everything with respect to time. So V, the derivative of V, is just 1. But since we're differentiating with respect to time, it's 1 times dV dt. I'll just write dV dt. Equals 25 pi, that constant, times, you got it, dH dt. And now, we're not done because we know what dV dt is. It's 3. So 3 equals 25 pi dH dt, or dH dt equals 3 over 25 pi meters per minute. So that is how fast it's increasing. 3 over 25 times pi meters per minute. And that's how we solve the big problem. Now, let me just erase this. And today, we're going to talk about linearization and differentials. Linearization is our linear approximation, as it's often called. If you remember, we talked about the idea of a limit way back at the beginning of chapter 2. And I drew a graph. And I said, you know, we're finding the tangent line. We're going to find secant lines that are closer and closer between 2 points P and Q. We have P and Q, and we've got the point A. We find P and Q closer and closer and closer, so we can find out the tangent line to A at that point. Well, this is kind of like an adaptation of that concept. Let's say we have a function. I'm going to pick the exponential function. Let's look at the exponential function. So, sort of like that. We know that this point right here is 0, 1. So let's say that point A is 0. We know that the derivative of the exponential function there is A. Or it's 0. Or wait, no. We know that we can easily compute the derivative right here. We know the value of A at 0. It's 1. That's simple. And the derivative is, of course, e to the x. But the question is, do you know what e to the x's value at 0 is 1. But do you know what e to the x is at, say, 0.01? I sure don't. Well, we're going to use linearization, linear approximation, to prove it. This idea is founded in the idea that any graph, the closer and closer you zoom in on the graph, if we take that function right there and we zoom in on it, we'll see that that little hump thing look at it there, and then we're going to zoom in even further. And you can see that at that point, let's call that magic point A, at that point A, the further we zoom in, the more the function looks like its tangent line. Now, if you've taken physics, you no doubt know about this. They often simplify sine theta, saying that sine theta equals theta, or sine x equals x, if x is small enough, and cosine theta equals 1, or cosine x equals 1, if the numbers are small enough. This is the idea of linearization. It's saying that something is about something else. Let's see it in practice. It might be a little bit easier. First, let me write the equation for you. Y, I'll explain it. Y equals f of a plus f prime a times x minus a. Okay? Also, that's the equation to the tangent line. The approximation is that f of x is approximately equal. If that is the tangent line to the function, then f of x is pretty close to f of a plus f prime a x minus a. So here you need a point A, and you need to know the derivative of the function. And that's how you're going to run an approximation. Let's see how this works. Our exercise is, here's f of x. F of x equals x plus 3. Oh, well, yeah, here. Let me reword this. we want to find the linearization of f of x is the square root of x plus 3. And we're going to use that linearization to approximate 3.98, the square root of 3.98. That looks terrifying, but it's not going to be that hard. Okay, so we need two things to figure this out. The first thing we need is we need to know the derivative of this function, and we need a point A. Okay? That's all we need. So let's figure this out. Okay? Let's figure this out. F prime x, the derivative of the square root of x plus 3, we already know that it's going to be x plus 3 to the 1/2 is f of x. So the derivative, just using the power rule, is 1/2 x plus 3 to the negative 1/2. So 1/2 square root x plus 3. Right? Follow me, that's something we've used for a while. Power rule. Technically there's the chain rule here, but x is just 1, so it doesn't really affect things too much. But there's our f prime x. We have f of x is square root of x plus 3. F prime x is 1/2 the square root of x plus 3, basically. Or 1 over 2 times square root of x plus 3. Now, here's what we can do with that. We want to approximate 3.98. We have f of x, but now we also have f prime x, 1 over 2 square root x plus 3. Now we can do some damage. We want to find that at a equals 1. This is given information. You don't know that. I'm just saying we want to find the linearization at a equals 1, and we're going to use it to find 3.98, square root of 3.98. We know that this is going to be a number that's kind of close to 2, right? Because the square root of 4 is 2. So 3.98 must be very close, but a little bit under 2. Let's figure this out. Well, the linearization, f of x, or f of 1, is going to be approximately equal or linearization of x, which we write like this, L of x, is basically f of 1 plus f prime 1 times x minus a, x minus 1. Alright? And this is just as simple as plugging and chugging. L of x is f of 1, okay? F of 1 is square root of 1 plus 3. Square root of 4, 2. Bam. 2 plus f prime 1. Plug in 1 into here. 1 over 2 times the square root of 4. Square root of 4 is 2. It's 1/4. Times x minus 1 gives us 8/4 minus 1/4 is 7/4 plus x over 4. Okay? So that's our linearization. 7/4 plus x over 4. Now, this is really simple. We know that we have 7/4, and we know that x is going to be 0.98. It's not quite there, so just plug it in. Make x equal to 0.98, and you get 7/4 plus 0.98 divided by 4. You're going to need long division, but you'll get the right answer. And the right answer is 1.995. That's a 5. Yeah. Okay? So, the general idea is if you ever want to find the linearization of something, all you need to do is say, okay, well, this function is pretty close to f of a, the number, plus f prime a, x minus a. And we use that whenever you've got something where it's really easy to find out what f is at a, but not quite so easy to find out what it is when it's really close. It was really easy to find out this function at 1. It's 2. It was really hard to find out this function at 3.98. When x equals 0.98, that's 3 plus 0.98 is 3.98. That was hard as hell to do. X equals 1, that's 3 plus 1, that's square root of 4. That's really easy. So using this formula right here, we were able to take something, 3.98, that we normally never could have done, and make it really easy by plugging in f equals a plus f prime a times x minus a. And that's the idea behind a linearization. Now, the idea behind a differential is fairly simple. A while back, I brought up the idea of a differential by saying that you couldn't necessarily treat a dy and a dx like a dy, like a quotient. But here, in the idea of differentials, you absolutely can. You remember dy dx is the same thing as saying f prime x, right? Hopefully you remember that. I wrote down all the different types of notation. Well, therefore, this isn't just saying that these two things are equal. It's literally saying that these two things are equal. In other words, dy dx equals f prime x. In other words, dy equals f prime x dx. Multiply both sides by dx. So you can actually use that now. Now, why would you want to use that? Well, I'll show you. It's best shown through example. We'll take this question right here. It's a wordy question. The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? Now, using a differential, you have to understand what it is. Over that dy dx is the change in y over the change in x. That's what it is. So, what we do is we take that question that we just had. The radius of a sphere is measured, found to be 21 centimeters, but there's a potential error of 0.05 centimeter error. Differentials are often used in this application, so let's go over it. Radius of a sphere. First thing we need to know, if the radius, we need to know the radius of the sphere to figure out anything. If we do, we know that the volume of the sphere, V equals 4/3 pi r cubed. We went over that last time. Now we know that the radius of the sphere is 21 centimeters. So let's just go ahead and plug in 21. Yeah. Well, we could plug in 21 centimeters in here and find out what we can know, but I don't really think that's what we're looking for. We're looking for the maximum error in the value of the radius. So what we need to do here is we need to differentiate. We get dv, not dv dt, dv equals 4 pi r squared. All right, we're not using dr. Just using differentials here. Not with respect to anything, just differentials. If r is 21, and dr is the possible radius change of the possible error, radius change in r, well, this is pretty easy to figure out. dv equals 4 pi times 21 squared times 0.05. That's the error measurement of r. also called dr. If it helps you understand this, it's saying we don't know anything about the volume of this sphere. We don't know the volume of the sphere. We don't really need to. What we need to know, we can figure out the volume of the sphere, but what we need to know is what the error is with computing this length of r, 21 centimeters for r. If we know that the error rate is 0.05 centimeters, let's figure it out. That means that it could change this much. Whenever you're dealing with change, you're dealing with the derivative. So, dv, we differentiate both sides. dv equals 4 pi r squared dr. dv equals 4 pi times 21 squared times 0.05. Basically means that dv is approximately equal to 277. That's centimeters cubed. So dv, marker's running out of ink, dv equals 277 cm cubed. Now, that's the error. Now, if we take dv equals 277 centimeters cubed, we have another thing that we can figure out called the relative error. This 277 centimeters cubed, if the radius is 21 centimeters, that's a hell of a huge error ratio. So the way that we figure out relative error is we take dv, delta v, over v. And we know that the change in v over v is approximately equal to dv over v. And, well, now we get dv is 4 pi r squared, and v, because we remember we just did that, 4 pi r squared dr, my bad, and v equals 4/3 pi r cubed. Well, if you cancel out all of these things, you'll get this all equals 3 dr over r. And we know that that would mean that 3 times dr is 0.05, and r, the radius, is 21. That's about 0.0024. And we can express this called a percentage error by multiplying by 100. That's the relative error. And the percentage error is just that times 100, or 0.24% is the percentage error. So those are some applications of differentials and linearizations and things like that. All right, now, that's it for Chapter 3. Next up is the test. So if you come back for the next lecture, it's going to be a test, 5 questions, all on differentiation. And thank you very much for joining. I have one last question for you. The big problem for the day is the following. The edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1 centimeters. Use differentials to estimate the maximum possible error, the relative error, and the percentage error in computing A, the volume of the cube, and B, the surface area of the cube. All right, I look forward to going over that next time, and take care, y'all.